Okay, so let's get started here. Today I'm going to talk a little bit about differential pairs. It's something that in past semesters when we've had more time, Professor Nguyen covers, but since we're a little tight on time this semester, I'm just going to talk about it here in discussion. Then I'll talk a little bit about Lab 6 and some of the things you need to get started. And then if we have time, I'll talk about cascode amplifiers, which is another analog circuits topic that we like to cover, but is not super important because if you do continue to study analog circuits, you'll see a lot more of cascode and differential pairs in classes like EE 140. So differential pairs are basically the type of input we use for most op amps. And so an example of a differential pair, a MOS differential pair is something like this, where we have two matched MOSFETs. In this case, they're both NMOS transistors. And there's going to be a lot to the circuit that looks new to you because we're used to, I guess, seeing bias networks that have kind of the four resistors, maybe R1 and R2, and then we have a source resistor and a drain resistor, or maybe no source resistor, but there's always that drain resistor. And so what you will see if you continue to study analog circuits is that oftentimes that bias configuration isn't used. And what we'll do is we'll use a current source to establish the bias current. And then that current source then kind of sets the operating point, and we can determine VGS and VDS from that. And so you'll still need some sort of load. And I say load because we know in small signal, these RD resistors are going to go to ground if this is VDD up here, right? But that load, as I'll talk about in a little bit, doesn't actually have to be a resistor. It could be another transistor. But in this case, we're going to just use two drain resistors. This is going to be M1 here. This is M2 on the right. And then our output is going to be taken differentially, which means that we're going to take this as VO1 and the drain of M2 is VO2. And then our input is also kind of thought of as differential. So I have two inputs, VI1 and VI2. Okay, so everything is done differentially here, which means that we're going to amplify the difference between signals, ideally without amplifying their common mode value. And so let's go over a couple of definitions here. So when I talked about differential input voltage, I'm really just talking about the difference between VI1 and VI2. So I'll call that differential input voltage VID. And like I said, I'll define it as just VI1 minus VI2. And so in your homework, you actually have a differential pair, but in your homework, VI2 is grounded. And so in that case, VI1 just becomes VID, right? Because we have VI1 minus 0 to get the differential input voltage. And so we can kind of write this another way and say that we take half of the differential input voltage and call that VI1, and then the other half of the differential input voltage will be on VI2, and there will be opposite signs of each other, right? So if we have some difference between the two, say there are 2 volts difference between the two, then we could say, the VI1 is 1 volt and VI2 is negative 1 volts. So they're equal and opposite. Then we can talk about the common mode voltage, which is like the average. And so the inclination is to think of this as a DC voltage, but really this doesn't have to be DC. It could vary with time. All that matters is that it's the same signal appearing on both VI1 and VI2. And so if we know VI1 and VI2, then we can figure out what the common mode voltage is by taking the average of the two. So if VI1 is 1 volt and VI2 is 1 volt, then the average is just going to be 1 volt, but the differential voltage would be 0. Maybe a better explanation is if VI1 is 1 volt and VI2 is negative 1 volts, the average is 0, so our common mode is 0. And that's often the case, but there are times when the common mode voltage is non-zero. So similarly to the differential voltage, we can write this is really just the common mode voltage, VICM1, or VICM plus VICM over 2. And so that basically allows us to rewrite VI1 and VI2 as some average value, which is a common mode voltage, plus or minus the differential value. So in this case, I will take VI1 is going to be the common mode voltage plus half of the differential voltage, and VI2 becomes the common mode voltage minus half of the differential voltage. So I'm basically just looking at the voltages relative to each other and using those differences between the voltages and the averages between the voltage to define or rewrite my input voltages. And what this does is this allows us to use superposition to analyze a differential pair circuit. And so similarly to a single transistor amplifier, we can define a gain. To do that, we need to talk about the output voltage. And so we can talk about the differential output voltage, because usually when we have a differential pair, we'll take the output, what's called differentially, which means the output voltage we're concerned with is going to be, say, VO1 minus VO2. Right, it's basically just the difference between the two drain voltages. So if we know the differential input voltage and the differential output voltage, then we can define the differential gain, which I'll just call AD, as the differential output voltage divided by the differential input voltage. We can also talk about the common mode gain. The trick with common mode gain is that it's actually defined differently depending on where you look. And so I guess the way Professor Nguyen has taught in the past is you can think of it as just the single-ended voltage, the single-ended output voltage, so VO1 divided by VCM1. Your book actually defines it a little differently, and so you can call it VOD over VCM, where we look at the difference between VO1 and VO2 as a function of VCM. And lastly, to look at how well our differential pair is operating as a differential pair, we can define something called the common mode rejection ratio. The common mode rejection ratio is called CMRR, is defined as the ratio between the differential gain and the common mode gain. Basically, how well does our amplifier amplify a difference between inputs while rejecting an average value that's between our inputs? Because we don't necessarily want to see any change at our output voltage when we get a common mode voltage spike or something like that. We only want to see a change in the output when we have a difference between our inputs. And so to analyze the circuit, we should first look at, say, the differential gain. So again, differential gain is the differential output voltage divided by the differential input voltage, which, if we're using the notation on the circuit schematic I drew, it's VO1 minus VO2 divided by VI1 minus VI2. And to do this, what we'll do is we'll use superposition to analyze this. And so using superposition, we'll break down this problem so that we're finding a couple of different gains, and then we will combine them to find the total gain. So first, we're going to find VO1 as a function of VI1. We're going to find VO1 as a function of VI2. Then we're going to look at the drain voltage of M2. So we're going to find VO2 as a function of VI1 and VO2 as a function of VI2. okay? So to do this, we will first, let's draw our small signal circuit for the first case. So define VO1 as a function of VI1. And so remember, in small signal, VDD is going to go to ground. So we're going to have our two drain resistors connected to ground. And in all of this analysis, I'm going to assume that the transistors are matched and the drain resistors are matched. In reality, they're not going to be matched, and a more general analysis can be done where you leave RD1 and RD2 as distinct separate resistors. But just for an introduction here, I'm going to keep them the same. And so remember, I had that current source as the tail, and if I'm in small signal, that DC current source is going to be turned off. And so since it's a current source, to turn it off, I'm going to open circuit it. So the tail here, which is kind of the sources of our two transistors, is going to be an open circuit in small signal. And then I want to find VO1, so that's this voltage here, as a function of VI1, which is this voltage here. And since I'm using superposition, I'm going to take my other source, which is VI2, and ground it. And so to analyze this, I'm actually going to use the T model, because the T model, turns out, helps us visualize this gain a little better. And so I'm going to put my my dependent current sources, and then my 1/GM. Then my input is right here. So VI1. And then going back to the other M2, I have my 1/GM. I have my dependent current source. And then I'm grounding the input, the gate of M2. And like I was saying, if we were doing this more generally, we would actually designate GM1 as the transconductance of M1 and GM2 as the transconductance of M2. But for the sake of this, I'm just going to assume GM. I'll write that up here. I'm going to assume first that RD1 and RD2 are matched. Let's call that RD. And then I'm also going to assume that GM1 and GM2 are matched, and just call that GM. And so what I can do here is, I'm actually not even that concerned with the specific value of these dependent current sources. I'm really just going to say these are small signal current sources. So that's going to be ID1, and that's going to be ID2, right? The drain currents for my two transistors. And so I'm kind of leaving those as general IDs. And then I can look at the current in this circuit. And so I see that my pen is acting up. This total current, which I'll just call this I can actually find the value of that current by just looking at the voltage drop across these two resistors, 1/GM resistors. And I can write that as VI1 minus 0, because the gate of M2 is grounded, divided by 2/GM. Right? I just use Ohm's law to figure out what that total current is. And so what does that mean? Well, I guess that if you're concerned about the direction of those current sources I drew, that just means that ID1 is equal to I tote, and that ID2 is equal to negative I total, right? I just drew those current directions conventionally going down, but in reality, when we're looking at this superposition. In this case where we ground the gate of M2, the current is actually flowing the other direction. So what am I concerned with here? I forgot to draw that. I'm concerned with, or I want to find VO1. Well, I know that there's really only one branch here. So the current going through RD up here is still going to be I total, because there's no current flowing in or out of VO1 or VI1 or into that ground node. And so to figure out the voltage VO1, I can again just use Ohm's law using this RD here. And so I can say that VO1 is equal to 0 minus the total current times RD. Well, if I plug in that I total that I found, then I get that the output voltage at the drain of M1 is just going to be equal to negative VI1 RD divided by 2 over GM. And so I'll rearrange this to get my first gain term, which is going to be VO1 over VI1. And I get that it's negative GM RD over 2. So we can see this looks similar to the gain expressions we've found for, say, a common emitter amplifier, or even if we looked at a common source amplifier, right? It's going to be something like GMRD, negative GMRD. But because we are taking a differential circuit, we actually get half of the gain for this one component. All right. So that's the first component of our gain. Now let's find using a similar method. I'll change colors. Let's find the gain VO1 over VI2. So let's find, how does the gate voltage at M2 affect VO1? To do that, we're going to draw the same circuit but now instead of grounding the gate of M2, we're going to ground the gate of M1, because we're going to use superposition to find the effects of VG2, which is the same as VI2 on VO1. So circuit's really the same thing we had before, just we're switching our inputs so that we're grounding VI1 and leaving VI2 in our circuit. And so similar analysis, right, where I can say that the total current here now is going to be, it's very similar, it's just going to be VI2 now divided by 2 over GM. And then now the total current is flowing the opposite direction through this RD connected to the drain of M1. And so I can say that VO1 is really just going to be positive I tote times RD. I'm going to skip a couple steps here, but doing the same exact math as I did before, I can say that VO1 divided by VI2 is going to be positive GM RD over 2. Any questions so far? So one thing I should, I guess, explain is the reason there's no current flowing into this ground node here is because I know that I'm going to have equal and opposite currents, drain currents in these transistors. If I look back at my original circuit, if I have actually, I'll go to this. If I have VI1 here and ground here, that basically means that the voltage across the gate to source voltage of M1 is going to be VI1 over 2. And then the voltage across the gate to source voltage across M2 is going to be negative VI1 over 2. Basically, that voltage is going to drop evenly across the gate to source of M1 and the gate to source of M2. And so if I have the same VGS and I have these transistors matching, that means that they're going to have the same drain current, but just equal and opposite directions. And so that means that all of this ID1 here has to flow back through this ID2 dependent source, which means that none of the current will actually leave this loop and flow into ground. So the last thing to do is basically repeat what we did, but to now look at VO2. And so I'm going to skip the math here because it's really the same exact thing. But we know that VO2 over VI2 is again going to be an inverting gain like we had for VO1 divided by VI1. And it's going to be the same thing. It's going to be negative GM times RD over 2. Similarly, VO2 over VI1 will have the same magnitude, but with positive gain, GM RD over 2. Now to combine all of this, right, we're looking for the differential gain. And remember, we said that's VOD or VID, which means it's going to be VO1 minus VO2 divided by VI1 minus VI2. And so if we look at VO1, we have combine these two expressions and say that VO1 is equal to GM RD over 2 times VI2, I'll say negative GM RD over 2 times VI1 minus VI2. I'm just combining these two expressions and taking the common GM RD over 2. Similarly, we can take our VO2 expressions and say that VO2 is equal to, I'll leave that term the same and I'll say that's GMRD over 2 times VI1 minus VI2. So then if we take those two expressions for VO1 and VO2 and plug them into our gain expression, we get the common term of VI1 minus VI2 times negative GMRD over 2 minus GMRD over 2. So that's VO1 minus VO2, and then remember we're dividing by VI1 minus VI2. And so we can cancel out those two terms and say that our total differential gain is just going to be negative GM times RD. Now that might seem like a lot of work to find an answer that seemed fairly obvious, but it's important to do this analysis and to understand for yourself why the differential gain is GMRD, or it's actually negative GMRD if we define it as such, because we're going to get an inverting gain. There's another way of analyzing this that in some ways I think is more intuitive, but I think that this method builds off of what you've learned in the past more consistently. So that method is called the differential half circuit. And if you take 140 or something like that, you will see that differential half circuit and see that there's other ways to analyze this. But for now, I'm just going to cover this method because I think it requires a little more guidance. Any questions about this? So I guess I should clarify the reason I was able to write VO1 here is because I need to combine these two terms, right? Because I'm doing superposition. So because we did superposition, we found these different components of the gain, but the total gain VO1 is going to be the combination of these two. And then we talked about, I mentioned common mode rejection ratio. And so the idea behind that, like I said, it depends on how you define common mode rejection ratio. But if we have a circuit like this that I've drawn here, what we would actually find is that if we have the same input on VI1 and VI2, so when I say the same input, I'm talking about something like the common mode voltage, then the resulting output on VO1 and VO2 is going to be the same, right? Because M1 and M2 we're assuming are matched, RD1 and RD2 are matched. And so there's no place for us to get a differential voltage between VO1 and VO2 if we have the same input on VI and VI2. And so in this case, common mode rejection ratio is infinite because we have an ideal current source. So I bias, the bias current source is ideal. RD1 is equal to RD2 and GM1 equal to GM2. Really, that's like KN1 is equal to KN2, right? The transconductance parameters. So like the devices themselves are matched. The physics are the same. Real quick, I want to just cover a scenario in which they would not be the same. And so I guess the first most obvious scenario is if RD1 is not equal to RD2 or GM1 is not equal to GM2, then you could find out the different gains for the two different branches, right? Because the gain depends on GM and RD. And so if the GMs and RDs are different, then I'll get slightly different gains. That means I'll have slightly different outputs at VO1 and VO2. And so I'll have some differential output that's non-zero. Another way, even if we have matched RDs, is if we, instead of using an ideal current source, another very common way of biasing is to use what's called like a tail resistance. So rather than a current source, I'm just going to have some resistor here. And this now looks, a little more like the bias networks we've seen, where we add a resistance to the either the emitter or the source, and then we have a resistance on the drain. And really, we're just kind of assuming that we're going to have some gate voltage, DC voltage generated here. But I'll call that resistance RSS, and I'm looking at the common mode circuit here. So I'm going to think about the inputs being equal. Then I have my two drain currents, ID1 and ID2. This is M1 and M2. And so I know that then if I have RD and GM matched, I can assume that the drain currents are still equal. So I'll just call that ID. And then the total current flowing through RSS is going to be ID2. And so this is an example of using a half circuit, but for the common mode. So if I have this circuit, I can actually redraw it. And this might make some people uncomfortable, but for now, trust me that this is allowed. And I'll explain why if you have more questions. So what I'm doing is I'm splitting this source resistance into two source resistances in parallel. And so if I combine these two in parallel, they need to equal RSS. So that tells me that each of them is going to equal 2 RSS, because then when I combine them in parallel, I'll get half of that value, and I'll get a total RSS that's just equal to RSS. But the reason I'm doing this is because what I find is that if everything is matched, so if this is ID and this is ID, that's ID, and that's ID, then all of that drain current is going to flow right past this connecting wire here. And the current in the wire is going to be 0, right? Because there's not more current flowing into either of the two new RSSs that I've created. And so if there's no current flowing through that wire, then that wire is not doing anything, and it's effectively not there. And so what I can do is then draw what I've been calling the half circuit, where now, instead of some differential circuit that I need to do superposition on, I can analyze a single transistor amplifier, which looks like something I've seen before and is much easier to analyze. And in this case, then, I can call this VO1. This is the common mode input voltage. And I can just use inspection to say that VO1 is going to be negative GM. Let's write it more generally. Negative big GM times RD. I'm neglecting R naught in all of these. I guess I should have said that earlier, but just know that I'm neglecting R naught because it's usually much bigger than RD. And so that's my effective GM. And I am going to have an effective GM that's actually less than my small GM because I have this RSS, which we call degeneration. So he's covered this for common emitter amplifiers. It's the same concept for a common source amplifier, where when I have this extra resistance hanging off of my source, what I get is, the way that I think about this is, I can apply my input voltage, and if there's no resistance, all of that input voltage is going to VGS. And VGS is really what's going to cause my current, right? GM times VGS gives me that drain current. Well, if I now have some resistance hanging off the source, now the entire input gets split between VGS and the voltage drop across that resistance. And so now my voltage across VGS is actually a fraction of my total input voltage. And so now I only get a fraction of my effective GM, of my total GM. And so usually what we can say is that if GM times 2 RSS is much bigger than 1, then this is approximately just negative RD over 2 RSS. And so what this tells us, so I should clarify, if we are defining the common mode gain as VO1 minus VO2 divided by VICM, I'm still going to get a common mode gate of 0 because there's no mismatch in the circuit. There's no reason for VO1 and VO2 to be different if I have the same VI1 and VI2. But if I look at the single-ended common mode gain, which is what this is, right? I'm not defining this as VO1 minus VO2. I'm just defining this as VO1. So I'm taking the output at one of my two drains. Then I get some common mode gain here that's not 0. And so I could similarly take my single-ended, here I have like my single-ended differential gain. And what I would find is that the single-ended common mode rejection ratio is not infinite, but it's actually much smaller. So when I do not use this amplifier differentially, then I'm not going to get a good common mode rejection ratio. So I'll just write that down here. So single-ended common mode rejection ratio is going to be my my VO1, say, divided by VID, and my VO1 divided by VICM. So I'm taking the single-ended input, or sorry, differential gain and common mode gain. And what that gives me, so if I look up here, this is my single-ended, because this is VID here, the differential input voltage. And so if I look at this expression, the single-ended differential gain is just negative GM RD over 2. Right? I get half of my total differential gain. And so I have negative GM RD over 2 divided by this single-ended common mode gain I just found, which is negative RD over 2 RSS. RD over 2 cancels, and I get like GM RSS. So that's much less than infinite. So the lesson here is if you are taking your output single-ended, your common mode rejection ratio is going to be much worse. Basically, the difference between your differential and your common mode gain is not going to be nearly as high. All right, lab 6. Let's talk about lab 6. So in lecture on Friday, Professor Nguyen covered kind of the basic idea behind cascading gain stages. And so really, I'm going to assume that you're going to have 4 separate gain stages because you have 4 transistors afforded to you. And so what do we care about? Well, we want, so we want high input resistance, Rn large. We want R out small for an ideal voltage amplifier. And we want gain large. And so that tells us that this first stage needs to have high input resistance. And then that tells us that the 4th stage should have small output resistance. And then the middle 2 stages, this is probably where we're going to get our gain, voltage gain. And so if one needs to have high input resistance, then there's a couple different options. But generally speaking, we probably want either something like a common emitter with degeneration, or maybe even just an emitter follower, which is a common collector. Because that will give us high input resistance, either of those stages. The output stage, really the main topology that we know of that gives us low output resistance is a common collector, or that emitter follower. that'll give us low output resistance. And then how about stages 2 and 3? Well, that's kind of up to you, but I will say that if we say we use a common emitter with degeneration for stage 1, then our output resistance of the common emitter, if you go back to the table that Professor Nguyen generated, tabulating the different relative sizes of each of these parameters for each topology, the output resistance of a common emitter with degeneration is kind of high. So that's not good. Because as we go from stage to stage, we want the output resistances to be small and the input resistances to be large. So generally, you know, we want something like Ri2 much larger than R01. And by extension, we want Ri3 much larger than R02. And then we want Ri4 much larger than R04. That's because every time we go between stages of gain, we will get a voltage divider. And the smaller that input resistance is with respect to the output resistance of the previous stage, the voltage divider fraction will be smaller. And so I'll just say stage to stage attenuation, which is the opposite of gain, right? Something smaller, is going to be generally Ri n plus 1 divided by Ri n plus 1 plus R out then. And so the bigger R out is and the smaller Ri is, the bigger this will approach 1. So this is always going to be less than 1, but we want it to be as close to 1 as possible. And so this is just trying to get you to think about, when you're choosing the topologies for these different stages, what you should factor into your decision. And so, yeah, I could make the first stage a common emitter with a generation, try and get some gain out of that. But if I have a high output resistance to my first stage, then I might lose a lot of that gain just going from stage 1 to 2. So I might want to use the common collector or the emitter follower, because its low output resistance will make this stage to stage voltage division smaller. And then if I look at the two stages, well, if they're both high gain stages, they're probably going to be either, I'll just say common emitter or common emitter with degeneration, right? Those are our highest kind of gain stages that we know of, topologies. And so if we use a common emitter for stage 2, that's going to have high output resistance. And so that might mean that stage 3, we use common emitter with degeneration, because we know that this has high output resistance. I'll say like medium input resistance. It's all relative, right? And so if we're looking at these two, common emitter and common emitter with degeneration, they both have high output resistance, but the degeneration actually increases the emitter input resistance of that stage. And so when you're deciding which stage to add degeneration, if you want to do that, you might consider the previous stage and how large that previous stage's output resistance is. Because the larger the previous stage's output resistance, the larger you want to make your next stage's input resistance in order to keep that attenuation factor as close to 1 as possible. Does that make sense? Another thing I can talk about is the output swing. So I'll probably go till 10 after. So if you have to leave, that's totally fine. But I just want to give you these kind of hints for your lab. so you can get working on it over the break. And so let's just say you have a stages 3 and 4 that look like this. So you're going to have some VCC, you're going to have a common emitter. And like I said, you might want to put degeneration here, you might not. But for this one, I'm going to use a bypass capacitor, which means this is going to be just a common emitter. And so I'm only looking at the last kind of 2 stages maybe. So this is my RC. So I have a common emitter, and then I'll put this into a common collector or an emitter follower, whatever you want to call it, where I have, I'll call this 3 and 4. So you know what where this fits into your total amplifier design. And then the output, of course, for an emitter follower is taken at the emitter. We'll add a coupling capacitor here, I can call CE4, and then we'll have our load resistance here. That's VO. And so just really quickly, let's think about this output. So the output swing VO, it's not really going to hit its upper limit, right? Because its upper limit based off of Q4 is really going to be VCC minus VBE4. So really the upper limit of VO is going to depend on VC3 here. So VO max is going to be VE4 max, which is VC3 max, right? That VC3 is going to set how high that VE4 can go minus the on voltage of Q4. So my emitter of Q4 cannot go higher than VC3 minus VBE4. And VC3, that's just VCC, the max voltage that VC3 can go. So this is a case where this output swing is actually dictated by the second to last stage. And so this is the kind of thought process that you need to go through. Now let's talk about VO min. VO min, again, is going to be determined by VC3 min. And that VC3 min, well, I have my VCE3. I have my VE3. And I know that VC3 min has to be at least VCE sat above VE3, right? Otherwise, Q3, excuse me, will go into saturation. It'll leave forward active, and we don't want that. So I look at VE3, and I say I want a buffer of VCE sat above that, and that's going to be the lowest that my collector voltage of Q3 can go. Well, VE3 for small signal is just going to be 0 because I have this CE3 grounding the emitter of Q3 in small signal. And so really, the minimum voltage, oh, sorry, I should correct this. It's going to be VC3 min minus, again, VBE4, right? I look at the minimum voltage that VC3 can go, and I subtract the on voltage of my Q4. Just want to write, okay, minus VBE4. And so really it's going to be 0 plus 0.2, say minus 0.7 or something like that. I'll say approximately equal to that. Again, I'm seeing that the minimum voltage of my output node is actually dictated by the bias point of Q3. Okay, so the other thing to consider, I won't go into the math, is just that your bias current in Q4 has to be large enough so that the output voltage VO can swing whatever the spec is. And so we'll get to that, I think, once we get a little further into this lab. But basically what we have is a set of another set of constraints that as long as we satisfy those, then we can look to these constraints and just be concerned with the bias point of Q3. The last thing I'm going to say real quick is if you've looked at your lab 6 spec, you'll notice that you don't just have a target FH that you need to be above. You actually have a target FH that you need to hit within 1 kilohertz. So a 5% kind of tolerance you have on that FH spec. And so I'll just say to hit your FH spec plus or minus 5%, you may need to use what's called frequency compensation. So you may need to insert a compensation capacitor. And what a compensation capacitor is it's an external capacitor with a small value. So it's not a bypass or coupling capacitor. So let's just say, generally speaking, I have some common emitter stage. And this common emitter stage, I know is going to have parasitic capacitances. So I'm going to have my C pi here, and I'm going to have my C mu here. Well, if I design this bias network to get the gain I want, but it doesn't give me the cutoff frequency that I want, especially if that cutoff frequency is too high because C mu and C pi are so small, what I can do is I can add an external capacitor, which I'll call this CC. I know we've used CC for coupling capacitors, but that's this compensation capacitor. At this point, then I get an FH that's approximately equal to the capacitance at node 1, right, times the resistance at node 1, plus the capacitance at node 2 times the resistance at node 2. And I can use the Miller effect to find my capacitance at node 1, and I'll say that, okay, I have C pi, and then I'm going to have C mu and CC. Right? Those are in parallel, so I can just add their values, times 1 plus GMRC. This means that I can pick this value based on the other variables in my FH equation. So based on R1, C mu and C pi, and R2 even, to set my FH to a specific value. So this means I'm no longer at the mercy of these parasitic capacitances that I don't have control over, but rather that I can control, ideally within plus or minus 5%, the exact location of my corner frequency by choosing a value for CC, kind of solving back for it based off of the rest of my circuit. And so compensation capacitors, they're used for a lot of different things. The dominant pole compensation we learned about in op amps is a capacitor added so that the open loop frequency response of your op amp has a pole at a low frequency. And that's done for stability purposes. This is just for your own knowledge. It's not something you're going to be tested on. But when you have an op amp, you want the feedback to stay negative. Otherwise, you might get instability and get oscillation. And so to do that, what you do is you add a pole at a low frequency so that by the time you get to your other pole, your higher frequency poles, right, at that point, if you go through two poles, you'll have an 180-degree phase shift. And so any negative feedback will actually get flipped and be positive. But if your low frequency pole is low enough, the gain at that point where your phase goes to 180 will have actually dropped below 1. And so the only case where I'm concerned about positive feedback is if the gain is bigger than 1, because that means every time a signal passes through the loop, it'll add because there's positive feedback, but it'll also grow because the gain is more than 1. If the gain is less than 1, sure, it'll be adding, but every time that component will get smaller and smaller because it's a gain less than 1, so it'll be attenuated. Don't worry too much about that. I know I just said a lot without writing anything, but that's another example of frequency competition you'll learn more about when you learn about stability and phase margin in an EE 140 class. Okay, I didn't get to cascode amplifiers with active loads. If you're interested in this, we can talk about it in office hours or something like that. It's not something that you're going to be tested on. It's just something I wanted to introduce because you'll see it later. Okay, so that's all I'm going to cover for today. Any questions? Oops. Got a chat. Nope, no questions. Okay, thanks. Thanks, everybody. Bye-bye.